first online lecture for COMP7010. We're going to see how this goes. The plan is to work through the chapters as we would do in the normal classes, and we'll have an interactive Zoom session each week to discuss any issues or clear up any confusions and so on. Otherwise, we'll sort of proceed pretty much as we have before. I'll also be letting you know on iLearn about changes to the assessments, which is not very much. So there's nothing much to worry about there. Okay, so let's see how we go here. So the topic this week is logic. And to start with, I'll just work through some of the early parts of this thing and split the lecture up into a few different videos. And I'll put the links to the videos up on iLearn. So what's this chapter about? Well, basically the idea is that we can think of logical statements or propositions as formal entities in this sort of proof system, and we're able to manipulate them kind of like we do with other parts of programs like functions and values and things. And the idea is that we can essentially equate things like functions that take arguments with things like theorems that take assumptions or premises. And so we'll see how we do that in this chapter. Also, we'll talk about things like how to represent conjunctions, disjunctions, so ands and ors. What does it mean for something to be false or negated? So this will be sort of where you can do inequalities, for example, not equal, and so on. We'll talk about if and only if, which is essentially just implication in two directions. And we'll talk about existential quantification. So that's the counterpart of universal quantification, which is the for all sort of quantifier. And in the latter part of the lecture, we'll talk more about extending this into other things. So if we have the standard practice for logic and things like that, classical logic, set theory, these sorts of things, we'll briefly touch on some of the relationships between those things. Okay, so let's start with the beginning here with propositions. So if we think about something that we've been writing so far in the course quite a bit, so an equality sort of statement like this, if we sort of execute this, we'll see that the 3 equals 3 is a prop, and you should think of the prop as the type of propositions. And the type of propositions is somewhat different from the type of other things, but broadly speaking, you can just think of it as a type. And so if something is of type prop, then it's expressing some logical proposition. So in this case, it's an equality proposition. In the next one, it's an equality as well, but it's quantified over the two natural numbers here. So you can see it's a prop as well. And in fact, all of the things that we've been writing in previous chapters to do with theorems and those sorts of things, they're all props too. We just didn't see the prop part explicitly. The important part to realize about props is that they're not stating things that are necessarily true. They're just stating propositions which you can maybe prove, but it might be that they're not actually provable. So this one here, for example, says that every nat is equal to 2, and that's just a prop, just like everything else. But if we set out to try and prove that, we wouldn't be able to do that. Similarly with the 3 equals 4 here, we're not going to be able to prove that that's true, but it still has a valid type. Okay, and as they're saying here as well, the the fact that they've got types is not the only thing. They actually have first class behavior, just like any other value in the in the language. So we can do things like here. We can define a theorem to right. So this is where we mostly required props here, is when we're defining a theorem with this name. We can say, well, its type is this prop here, and in this case, the proof is very simple. But you can use propositions as values in other sort of contexts. So here, for example, we're defining a thing called plus fact, which itself is defined to be equal to the proposition 2 plus 2 equals 4. So if we define that and then check it, we'll get that that's a prop. So it's just giving a name to this proposition. And just like you can give names to numbers or strings or other things in COC, you can give names to propositions. And that's essentially what a theorem is doing, to be honest, as well. So here, for example, we could say that this theorem is just plus fact, which is 2 plus 2 equals 4. So when we get into the proof, if we were to do something like unfold plus fact, we would see that it's just 2 plus 2 equals 4, and the reflexivity here will do that for us, so we can just prove that trivially as well. And things like parameterization and so on are sort of essentially what you would expect for just like functions. We can define a parameterized prop in this case that takes a natural number as a parameter. So in this case, the proposition is that the number that's given is equal to 3. Right. And if we check the type of is 3, we'll see that it's not a prop, it's a nat to prop, because there's a parameter for this proposition. Okay, so that's sort of the basic idea. Now, when we use this in a sort of more formal setting, we can express what are often called properties of their arguments. So, they're also called sometimes relations. So in this case, injective, we've seen before in the general sense, we've said that data constructors are injective, for example. So if applying the constructor to two things is equal, gives an equal result, then it must be that the two argument values are equal. So in this case here, f of x equals f of y implies that the x and the y must be equal. Okay, so constructors are injective, but not all functions are injective. Some are, some aren't. So in this case, what we're doing is we're defining a parameterized proposition, parameterized over the function and the types of the argument and the return result, A and B, and it's defined to be the definition of injectivity. Okay, so that's just a definition of that property. And here is a proof, or here is a theorem that says, well, we can prove that the successor constructor, the S constructor for natural numbers, is injective. And the proof is similar to what we have seen before. We can basically use the built-in properties of constructors via the inversion tactic to say, well, if we have that S of n equals n S of m up here, we can invert that, and that gives us that n equals m, right? Because S is injective by definition. Okay, so it's not a terribly interesting theorem because we already know that every constructor is injective. But if we didn't know for a particular function that it was injective, we could state this lemma for that function and then try and prove that that's the case. Okay. The last point in this section is that the equality that we've been using is not really a built-in thing, actually. It's really just shorthand for this, something called EQ. Okay, so EQ, n equals m is shorthand for EQ and m, and you can see from this check down here, if we put the ampersand in front, so the at in front of the EQ, we get the full type with all of the arguments in there. So there's a type, which is the type of the two other arguments. So we take a type and two values of the same type, and that gives us a proposition as well. So that's the underlying stuff that's going on for equality. We haven't seen the definition of that yet, but we will see that later. But the equal symbol is just an application of this EQ constructor, essentially. Okay, so that's props. We'll stop there for this one and pick up in the next video with logical connectives.